Hello friends, welcome to the online lecture series of St. Andrews Institute of Technology and Management, Gurugram. Myself Satinder Vats, Assistant Professor in ETC Department. In today's video, we will see about the sampling theorem, which is used to convert the continuous time signal into discrete time signals. It is a topic of Unit 2nd of Signals and Systems, EE 4th semester. So, sampling is the process to convert analog or continuous time signals into discrete time signals. So, continuous time signals are the signals or analog signals which are continuous in both amplitude and time, whereas the discrete time signals are the signals which are continuous in amplitude but discrete in time domain. So, processing discrete time signals is more flexible and is often preferable to processing continuous time signals. So this is the reason that is why we perform the operation of sampling to convert the continuous time signals into the discrete time signals. So under certain conditions which we will see later, that a continuous time signal can be completely recovered from the samples or the sequence of its samples. That is, if we want to recover the original signal from the discrete time signal, that is the sampled signals, then we can do that under some certain conditions. So representation of a continuous time signal by its samples. Let's see. In absence of any additional condition or information, we would not expect that a signal could be uniquely specified by a sequence of equally spaced samples. So we need certain criteria so that we can recover our signal from the sampled space values. Okay, for example, if there are three different continuous time signals and are sampled at a particular rate, so there may be a situation where we would not be able to specify between three signals. That is, if we sample all these signals at the same rate, there may be a possibility that we would not be able to recover the signals. So if we have three signals, x1t, x2t and x3t, in which we have sampled it at a time instant of t. So we can see in the picture, like if we have three signals, that is, this is x1t, this is x2t and this one is x3t. So if I take samples at these instant, that is at t is equal to 0, then after time t, then after 2t, then after 3t, so we can see all of these three signals have the same value at that instant. So I would not be able to recover my original signal because all these three signals have the same value. So an infinite number of signals can generate a given set of samples. Okay, so we can have a number of infinite signals for these values. So it is very difficult to get the original signals. Okay, so we will see if a signal is band limited and if its Fourier transform is 0 outside a finite band, like this. If we have a signal which is band limited, that is minus omega m to omega m, which is 0 outside this range. Okay, so a signal which is band limited, that is its Fourier transform is 0 outside a finite band of frequencies, and if the samples are taken sufficiently close together in relation to the highest frequency present in the signal, then the samples uniquely specifying the signal we want to reconstruct it perfectly, reconstruct it perfectly. So this result is known as sampling theorem. That means we need to take the samples at a frequency which is nearly equal to the highest frequency fm, that is the message signal frequency, and this is the sampling frequency. So fs should be equal to or more than that fm, which we will see later the exact relation. So and we need to sample a signal at close instants, that is we need more number of samples so that we can recover our original signal correctly. Okay, so this is the sampling theory, that we need to perform the sampling at a certain rate, so which we will see later. So if I sample our signal at these instants, that is these samples are very close to each other, so it would be possible to get the exact recovery of that signal. Okay, so we do it using impulse train. So this is, that is why it is called impulse train sampling. So it is convenient way to represent the sampling of a continuous time signal at regular intervals. Okay, we would need to take the samples at regular intervals. It uses a periodic impulse train for that purpose and multiply it with a continuous time signal xt. So if our xt is our message signal, to get the sampled values of this xt or to convert it into time domain, we will multiply it with a impulse train. Okay, so this mechanism is known as impulse train sampling, and it is depicted in the figure that we will see on the next page. The periodic impulse pt, if pt is the periodic impulse train, it is also called the sampling function with a time period t, which is the sampling period, and uh, frequency, that is sampling frequency, is given by 2 pi by t. So omega s is equal to 2 pi by t, or if I represent it using this, fs would be 1 upon t. Okay, so this would be the sampling frequency of the sampling pulse. So in time domain, the sampled version of the signal, that is xpt, can be represented as multiplication of xt, that is the message signal, and pt, that is the pulse train. So pt is a train of pulses which can be represented as this impulse train, that is del t. This is the impulse function. If I say del t minus n t, then we will have samples at the multiples of n. This is t, this is 2t, similarly 3t, and up to nt, from minus nt to nt. So this is the train of pulse. Okay, so pt, that is the train of pulse, can be represented using this. So how can we generate the sampling signal or the sampled values of the signal? So we would take the message signal and multiply it with the impulse train, that is pt. So we get the xpt. So because sampling property of unit impulse, we know that multiplying xt, that is if we multiply xt with delta t minus t naught, which is a shifted impulse, so it would become x of t naught, that is where the pulse is positioned. So we would get the value of xt at t naught into delta t minus t naught, which we have already seen in the first unit, this impulse function and its properties. So xt into del t minus t naught would become xt naught and del t minus t naught. So if we have our message signal xt like this, and this is the pt, that is the impulse train of pulses, so xpt would be this, that is these sampled values will have the amplitude of the signal xt at the instant where is the pulse is. So wherever we have a pulse, that is at this instant, we will have the amplitude of this matches signal. Similarly, if pulse is there, we have this magnitude or amplitude. If pulse is there, we would be having this magnitude. So magnitude of the sampled train, that is this, would depend on the magnitude of matches signal. So figure shows xpt is an impulse train with amplitudes of the impulses equal to the samples of xt at intervals spaced by t. So we would have samples spaced at time t, or frequency would be 1 upon t. So if xpt is our this signal, that is x nt into delta t minus nt, which is the multiply of message signal and the impulse signal, this is our xpt. So if I take the Fourier transform, so multiplication would result in convolution in frequency domain. If I have multiplication in frequency domain, then it will result in convolution in time domain. If it is convolution in time domain, then it will be multiplication in x omega del omega in frequency domain, and vice versa. So using that convolution property, we have xpj omega is equal to, which is the Fourier transform of xpt, and pj omega is the Fourier transform of our pt signal, that is del t minus n t. Okay, so this is the Fourier transform of pt. Similarly, since convolution with an impulse simply shifts a signal, so we know this property that convolution of a signal, that is xj omega, if I convolute it with the impulse signal, it will simply shifts the signal. That is what where previously I was having xj omega, then after convolution I will be having xj omega minus omega naught, that is the frequency shifted by omega naught. So using this property, we will be having xpj omega, which is the product of xj omega and pj omega, as 1 upon t summation k minus infinity to infinity x of j omega minus k omega s. So this is xpj omega is a periodic function of frequency omega consisting of a superposition of shifted replicas of xj omega. So this is our xj omega in frequency spectrum. Okay, where the frequency is minus omega m to omega m. This is a band limited signal. So xj omega is the frequency. Xj omega is the counterpart of xt in frequency domain, which can be represented as a band limited signal. Okay, whereas pj omega is the impulse train with frequency omega s. So our xpj omega, that is our sampled signal in frequency domain, will look like the periodic signal with the superposition of shifted replicas of xj omega. So it will be having the replicas of xj omega, that is this, at frequencies omega s, 2 omega s, 3 omega s, minus omega s, and so on. So if omega is greater than 2 omega m, that is, this is omega m and this is omega s. If this omega s is greater than 2 omega m, so it will look like this. Otherwise, if omega s sampling frequency is less than 2 omega m, that is twice of this signal, then it will look like this. So we can see, if we do our sampling, if we take the sampling frequency omega s greater than 2 omega m, so we can reconstruct the signal in the original form. Okay, we will get the exact signal which I was transmitted. So if omega is less than 2 omega m, then we may get a overlapping of signals, that is, we may get this type of overlapping. so I would not be able to get the exact original signal if the sampling frequency is less than 2 omega m. So this is the sampling criteria or the Nyquist criteria, that is omega s sampling frequency should be greater than 2 omega m. So this is very important. So now we can define our sampling theorem as let xt be a band limited signal with xj omega is equal to 0 for omega greater than omega m. That is, if this is our signal minus omega m to omega m and it is 0 for other frequencies, that is 0 for omega greater than omega, that is this part and this part. So this is our xj omega. Then xt is uniquely determined or it can be recovered uniquely from the sample signal x and t, where n is equal to 0 plus minus 1 plus minus 2 if omega s is greater than 2 omega m. So sampling frequency should be greater than the twice of maximum of message frequency, and omega s can be given as 2 pi by t. Given these samples, we can reconstruct xt by generating a periodic impulse train in which successive impulses have amplitudes that are successive sample values. So we will see how we can regenerate our message signal. This impulse train is then processed through an ideal low pass filter. So we would use a low pass filter at the receiver end to get our original message signal with a gain T and cutoff frequency greater than omega m. So this low pass filter will have a frequency, cutoff frequency greater than omega m, less than omega s minus omega m, and the resulting output would be a signal exactly equal to our message signal xt. Okay, so here we can see if this is our xt message signal, this is our impulse train. If we multiply it, we will get the sampled signal, sampled train. If at the receiver end I pass it through a low pass filter, then I would get the received signal xrt, which is exactly equal to the transmitted signal xt. So this is our xj omega, that is the our message signal in frequency domain, which is a band limited signal, and this is our Fourier transform of the sampled train, that is a sampled signal which is having a frequency omega s which is greater than twice of omega m. Okay, so if I will pass this signal from a band pass signal, a low pass filter whose frequency, it will pass the frequencies greater than omega n and less than omega s minus omega m. So this is a low pass filter. So when I pass our sample signal from this low pass filter, I would get the message signal in the exact form. So this is how we can reconstruct our signal if we have sampled it with a frequency omega s which was greater than twice of omega m. So this is the system for sampling and reconstruction. This is the frequency spectrum of xt. This is the spectrum of xpt, that is the sampled signal. This is the spectrum of our low pass filter, and this is finally the received signal which is exactly same as the original xt. So this is all about the sampling, how we can generate a sampled value or a discrete signal from the continuous time signal at a frequency omega s which should be greater than 2 omega m. So this is the condition for sampling. So this is it for sampling. Thank you very much.